In this video, I want to revisit Le Chatelier's principle, but I want to do so in a quantitative manner. So you may see some practice problems that look like this, but this will also give you another way to think about how reactions shift when they are at equilibrium and you perturb them in some way. So this problem right here is the one that we just solved in the last video, and from the problem, we know that this reaction, I think we're at 100 degrees, has a Kc value of 0.36. And when we solved, so I'm just going to write E again, because we solved for the actual concentrations at equilibrium. The N2O4 concentration was 0.4083, and the NO2 concentration was 3834. So what I want to do is, to the reaction at equilibrium, add 0.2 molar/moles. We're not going to change the volume, so I think technically we might want to say moles, but basically we're going to increase the concentration by 0.2 of N2O4. So from what you already know about Le Chatelier's principle, if this is my reaction at equilibrium and I increase the concentration of a reactant, which way does the reaction shift? Hopefully you said that the reaction shifts to the right? It's going to minimize that disturbance that we put in. It's going to rebalance the reaction so that the products over reactants have the equilibrium constant ratio. Now, we can solve for what the new equilibrium concentrations would be with everything that we already know. So I have a set of equilibrium conditions right here. I am going to do this addition, right, that's described right here. I'm going to add 0.2 to the concentration of the N2O4. I'm not going to add anything to the NO2 because it's not listed in the problem. And when I do this, before anything happens, my reaction has 0.6083 and 0.3834. So these are kind of like, I'm going to say I new. So it's a new set of initial conditions. Now, we know that the reaction's going to move. Because of Le Chatelier's principle, it's going to reestablish equilibrium. We also know which direction it's going to move. So in terms of following the steps to solve this equilibrium problem, we know from understanding Le Chatelier's principle, it will move to minimize the disturbance. It will move to the right. But because we've now talked about reaction quotients, you could find Q. And when you find Q, you should find that Q is now less than K. Right? We made the number in the denominator bigger, so my reaction needs to move to the right. So there will be some change in my reaction, and I will lose reactant. I will make product according to the stoichiometry of the reaction. And then I will have some new set of equilibrium conditions plus 2x, and you have all of the skills that you need to solve this problem, right? The balanced reaction is still the same, so my equilibrium constant expression is still the same, and I haven't changed the temperature, so my equilibrium constant is still the same. So if I were to set this up, I would have 0.3834 plus 2x, that whole quantity squared, divided by 0.6083 minus x equals 0.36. This is an algebraic problem that I have the skills to solve. So I'm going to get all of this set up. I won't show you the quadratic part, but you should check to make sure that you can get the same answers out of the quadratic formula. So if I cross multiply and do some expansions, I end up with 0.218988 minus 0.36x equals 0.146996 plus 1.5336x plus 4x squared. This, rearranged, is 4x squared plus 1.8936x minus 0.07192 equals 0. And if you solve this with quadratic formula, the two values of x that you get are negative 0.50878. So you can see pretty easily that's going to be rejected, and 0.035375. All right, so this negative one gets rejected. And this is our x value. So plugging that back in to my new equilibrium row, my new equilibrium concentrations after my reaction got to equilibrium, then I perturbed it, then it reestablished equilibrium, is that the N2O4 is 0.5729 molar, and the NO2 is 0.4542 molar. And this is a lot of steps. This is a lot of math. One way that you can check your answer, take a minute to see if you can think of what you might be able to do. We have equilibrium concentrations. We're saying that this reaction is at equilibrium. Well, that means that these concentrations, when I plug them into my KEQ expression, should equal the equilibrium constant. So I should be able to do 0.4542 squared divided by 0.5729, and please check this in your calculator, it equals 0.36. So this is how we know that the concentrations that we got once it reestablished equilibrium are the correct concentrations.